Thank you, Don. Hello, I'm Ganesh by Mangalore. I'm a research assistant in the Human Performance Lab at UMass, as well as the UMass Transportation Center. Our project being presented today is the risk awareness and perception training using VR headsets, the validation of VR headsets to measure hazard anticipation behaviors. I would like to quickly introduce you guys to the team. Our research team is myself at the top, that's Ganesh by Mangalore, research assistant Yalda Ibadi, Professor Sibi Samuel, formerly of UMass, and professor right now in systems engineering at the University of Waterloo in Canada, Professor Mike Nodler, Professor Donald Fisher, and Professor Cole Fitzpatrick as well. So the Human Performance Lab, just a second. All right. The Human Performance Lab and the UMass Transportation Center are usually two collaborative labs that work with driving simulation, transportation and safety, human factors, and engineering. The training, the project focuses on risk awareness and perception training. What RAPT is it's a popular training program that concentrates on hazard anticipation and poor scanning behavior and tries to improve these skills in novice drivers. It first appeared in Fisher et al. 2002. Results from RAPT showed that RAPT-trained drivers were twice as likely to detect hazards and hazard zones and situations when compared to the untrained ones. A fully dedicated RAPT for VR is yet to be designed, particularly because the VR headset driving simulator has not been validated for hazard anticipation yet. Hence, this project aims at validating the VR headset platform by testing hazard anticipation behavior of the drivers, and also hopefully designing a VR version of RAPT somewhere down the line in the future. Why do we need VR headsets? Why can't we just stick to our favorite old fixed-base driving simulators? One thing VR does is it's really cost effective. It's also super portable. You can move it around in a handbag, and that's great because you can't do that to driving simulators. Networking is much easier. That means you can connect to multiple VR headsets and multiple driving simulators that are running on VR headsets. Also, the realism and immersion of these headsets is really great, particularly because it's got modern day graphic capabilities that are realistic when compared to driving simulators, which are less realistic and less immersive. Also, game engine and great interface in general. Unity and Unreal engines are both used to design VR and VR virtual reality worlds, and they're really user-friendly as long as you know C# and C++. But building worlds and scenarios on game engines has particularly been one of the best times I spent on this project. What is the potential that VR holds if validated? As driving simulators with the same fidelity as the fixed-base simulators, if validated, it's going to be great when compared to fixed-base simulators, particularly because of the portability and the less space requirements. It collects, if validated, it would be collecting all sorts of data like eye measures, vehicle measures, behavioral measures. Also, as said before, it would have ultra-realistic graphical qualities for the fully immersive experience. It would also connect to multiple drivers, and we could also have multiple modes that we are not just confined to driving simulator. We could have a pedestrian simulator. Work on such things are already being done right now for the pedestrian simulator and the bike simulator. What are the challenges though? So we do not have any documented research of VR use for driving simulation. At least we didn't have when the project was started. Also, there's lots of reports of simulator sickness with VR headsets, not just as a simulation, not just as a driving simulation tool, but also has even at gaming, some people just feel too sick while using the VR simulators VR headsets. So we got to test out whether they are good enough to measure driving measures such as vehicle measures and behavioral measures. And also we have to keep in mind that we should not have a lot of attrition rates due to simulated sickness. So that brings us to the goal of the study, which is to compare the difference. There'll be three issues that will be tackled in this study, three major ones. That is, the first one will be to compare the difference in the proportion of latent hazards detected by middle-aged drivers compared to younger drivers on the VR driving simulator to the same difference on the RTI simulator. I'll get to why we've chosen these particular variables later on. Comparing the average and total glance duration of younger and middle-aged drivers on the VR simulator compared to their counterparts on the RTI simulator, and also to see if the rate of if the severity of the simulated sickness for younger and middle-aged drivers on VR is similar or worse when compared to their counterparts on the RTI simulator. So first we get to hazard anticipation. Why we've chosen hazard anticipation apart from its obvious links to RAPT? One is because younger and novice drivers lack the ability to anticipate hazards compared to older experienced drivers, where Pradhan 2005 showed that about 70% of the older drivers detected latent hazards, while only about 26% of the younger inexperienced drivers detected the same hazards, and only 40 of the younger experienced drivers were able to detect the same latent hazards. Why latent hazards are important? Because the inability to detect latent hazards has been linked to crashes. A study by McKnight in 2003 showed that out of 1,000 plus crashes reviewed, failure to detect hazards accounted for like 42.7% of the crashes. Next we go to glance duration. What is glance duration? It's basically how long a person fixates on a particular object in for his one fixation, basically. It's going to be explained better later. Right now I'm just hazy on the term, but with glance duration, it's known that older drivers spend longer in total looking at latent hazards than their younger parts. It was confirmed by Urweiler 2015 and Krundal. It has also been reported additionally that only marginally significant differences in average glance durations when compared to average glance durations of middle-aged and younger drivers, confirmed by Chapman and Underwood and Chan et al. These terms will, I promise these terms will be explained better later on into the presentation. So let's get into the apparatus right away. So on the left side we have the fixed base driving simulator with the ASL mobile eye tracker, and on the right side we have the VR headset based driving simulator. That's the combination of the Tobii HTC Vive integrated headset that's got eye tracking integrated in it as well, and also the Logitech G29 steering wheel. On the fidelity side, as you can see, the RDI driving simulator is quite high, while the VR headset is low. Also, the vehicle measure outputs. The RDI driving simulator collects a lot of the vehicle measures when compared to none on the VR headset. The none is basically subjective because they can be programmed to collect the desired output, but I just didn't do it for this experiment because we were focusing on hazard anticipation. Eye tracking can look at, for the ASL mobile eye, the eye tracking can look at blink rate, dispersion, gaze direction, and gaze point, while for the VR headset integrated with eye tracking, all these functions are programmable, but we only looked at gaze point, gaze direction, and glance frequency and duration. The refresh rate is almost the same. The field of view is fixed for the simulator, that's 330 degrees. It's 110 for the VR headset, but it's relative to the user's head position. So it is possible to get a perception of a full 360 degree view. Just that it's got really low latency and it moves along with the user's head, so they'll probably feel like it's 360 degrees. Participants and demographics. We recruited 48 participants with a valid US driver's license. On both simulators, we had 12 young drivers and 12 middle-aged drivers. The average age of young and old drivers, young and middle-aged drivers, was almost similar for both platforms, as well as their driving experience. The experimental design was a 2 into 6 mixed with platform and driving as 2 between subject factors and scenario as a within subject factor. 4 groups of participants, as mentioned earlier, navigated through 6 scenarios on the assigned platform. The order of the scenarios were counterbalanced across and within groups using a balanced latent square method. Just a second, I'm sorry. The scenarios were, the first scenario was the driver approaching a stop sign near a building block where a pedestrian has been obscured by the building block, so the driver would need to scan onto his right side to look at the driver. I could explain the scenarios all day. I'm just going to explain the scenario what we're going to look at later on. That's the third scenario in the middle on the left. That's a driver approaching a parked truck along with passing vehicles on the left side of their travelway. The parked truck obscures the pedestrian up to a point where the driver cannot see it until they approach the crosswalk. I'm going to show you guys a video of the scenario I just explained in a couple of slides, but I'm going to explain the procedure first. We gave in a pre-study questionnaire to record the demographics and driving experience. The basic instructions were first given to the participants about what the study was about. We did not give in too much information to prevent bias. The participants were then given a short tutorial about the controls of the steering wheel on the VR-based simulator, but also on the driving simulator, the RTI driving simulator, for the participants who have never driven a simulator before. The eye tracking calibration was done for both VR and the mobile eye tracker. It's a 9-point based calibration. Practice drive was then allowed so that the participants can get familiarized with all details of the simulated experiment, and once they were ready, they were put through 6 scenarios for the next 45 to 50 minutes. At the end of the study, we handed them a simulated sickness questionnaire and a post-study questionnaire for the VR participants to record any simulated sickness symptoms and also to monitor user experience of the user experience attributes. It's worth mentioning that they were also given the simulated sickness questionnaire at the beginning, but the starting simulated sickness severity ratings are next to 0 with a few minor differences, so we did not consider the pre-study simulated sickness responses from the participants. We only considered the post-study simulated sickness responses. As you can see, this is the simulated sickness questionnaire. It's got 27 different symptoms with 16 that are with 15 to 16 that are actually of interest. They can be rated from 0 to 3, from none to severe. The total score will be calculated. Alright, let me get into much detail. So the disorientation scores by one of the participants was 2, 2, 3, 2, 3, 2, and 1, which was 15. The weighted score for the disorientation was 15 into 7.58. Whatever that is, I don't want to do quick math right now. But similarly, the weights for N and D are 9.54 and 13.92, and the total score will be equal to N plus O plus D into 3.74. 3.74 is the weighted score for the overall score. So we put this in, and I'm going to explain what the analysis process was later. This is the post-study questionnaire about 7 different attributes regarding user experience. It could be rated from 1 to 5. Next, what are the analysis techniques for hazard anticipation? So for hazard anticipation, we used binary coding, but the binary coding was also dependent upon the launch zone and target zones. So what it means is, if the participant looked at the latent hazards or detected the latent hazards, they would be scored as 1. But that glance or look at the hazard wouldn't be counted unless they were inside a launch zone that started 50 feet before the transpiring of the hazard. The target zones are basically the hazard zones, while the launch zone starts 50 feet before the hazard. And this is scenario 3, as I explained earlier. So scenario 3 has 2 target zones, one on the left side of the crosswalk, which is partly obscured by passing traffic, and on the right side of the crosswalk, where the pedestrian is obscured by the truck. So the driver cannot see the pedestrian unless he reaches towards the front of the truck at the beginning of the crosswalk, but the launch zone begins much well ahead of that. So we are looking for scanning behavior at the beginning of scanning behavior before reaching the crosswalk. Here's an example video of that drive. This is captured on the RTI simulator, and a similar video will be shown later on for the VR driving simulator. I'm sorry if the participant speaks during this drive. I haven't actually seen it completely. So right about here is the beginning of the launch zone, and you can see that the participant is scanning to his right and left side to detect latent hazards, and they detected the pedestrian behind the truck, and they passed along safely after detecting both hazard zones. That's what we're trying to see here. Similarly for the VR headset, it's built in Unity, and it's worth mentioning that both these participants were older drivers, and hence they had much better scanning activity than the younger drivers.
Turn right.
So you see this participant, the launch zone starts now, and the participant is scanning both sides of the crosswalk as well, and they stop by, they see the pedestrian, and they keep going as planned. So that was how we coded the hazard anticipation behaviors. Glance duration. So here's what glance means, right? So one or more sequential fixations on the target zone when the participant is inside the launch zone. Total glance duration is the sum of duration of all glances at the hazard, while the average is the mean duration of all glances at the hazard. We used software called Boris for frame-by-frame analysis of each recorded video. So the 2 videos you saw earlier were imported into Boris, and they were analyzed frame by frame to see if there was a glance on the hazard and glance off the hazard, and how many glances were made. One frame is equal to 33 milliseconds. So the analysis goes, as you saw before for the previous video, the analysis goes, the first glance began, the first picture right here is before the participant has glanced at the hazard. They are looking at the bush, which is not exactly the hazard zone. The hazard zone is the front edge of the truck. So in the second picture, in the middle, they begin looking at the other side of the crosswalk. So we take that frame as 3,453, and in the next frame, they are not looking at the hazard zone. So we count that as 3,473. That is The middle one was an on glance, and the extreme right one was an off glance. So 3,473 minus 3,453 is equal to 20 into 3 is the glance lasted for 660 milliseconds. And the second glance was started at the frame 3,477 and it ended at the frame 3,496, lasting a total of 627 milliseconds. So for the two glances that we just saw, the total glance duration was 1.28 seconds or 1,287 milliseconds, and the average glance duration was 0.64 seconds. So that's the difference between total and average glance duration. So statistical analysis, we conducted a logistic regression for the binary scored hazard anticipation, as you see from the plot right now, which is the percentage of hazards detected by young and experienced drivers. 63.9% of the young drivers were able to anticipate. The young drivers were able to anticipate 63.9% of the hazards, while the older drivers were able to detect 91.7 on the full-scale simulator, while for the VR headset it was similar numbers with 62.5 from the young and 90.3 from the old. This is what you find out, as I just mentioned. The logistic regression results showed a highly significant main effect of driving experience or age, which meant that, in line with previous literature, the older drivers were much better than younger drivers at detecting the hazards. There was no significant effect of platform, which was great because now that says that there's no difference between the both platforms, and there was no second order interaction between driver experience and platform. There was a significant effect of scenario type, but there was no significant second order interaction between scenario type and platform. For the total and average glance duration, we used factorial ANOVA. Main effect of driving experience was found yet again for total glance duration, as Urweiler reported that older drivers spend much more time staring at the hazards than the younger drivers. There was no main effect of platform, which is great again because there's no difference between the two platforms now. There was no interaction between experience and platform either. For average glance duration, there was no interaction between platform experience, no main effect of platform, and no main effect of driving experience either, which is in line with the previous literature, which says that on an average, both younger and older drivers stare at the hazard, glance at the hazard for the same amount of time. The statistical analysis for the simulated sickness course was also a factorial ANOVA. As you can see here, just from the graph itself, older drivers did worse on their responses on the simulated sickness questionnaires, which is in line with past literature, which states that as people grow older, they are more susceptible to simulated sickness. There was no main effect of platform, once again, which is great because this shows how similar the full scale and the VR simulators were, and there were no second order interactions found either. For the post-study questionnaires, there was a main effect of driving experience on controls, as well as the same on the platform. The driving controls, one of the main complaints of the driving controls for the VR simulator was it was gaming steering wheels. So it was much less realistic than the RTI driving simulator steering wheels, which functions the same way as a commercial vehicle. So a lot of the complaint for the driving controls for the VR simulator was about the usage of the gaming wheels, which can be changed by investing in a more non-gaming oriented steering wheels. There was a main effect of platform for navigation. The people on the VR found out that they were a little confused with just voice navigation, which was different from the RTI because they were navigating with on-screen instructions, but due to the way Unity works, I had to code in voice instructions for navigation rather than on-screen instructions. Discussion. The results of the latent hazard anticipation were consistent with previous literature and with no impact of platform on either age group. Results were consistent with past literature and adds more evidence in support of VR headsets. Main effect of driving experience is for the simulator sickness. Oh, I'm sorry. So the first point was with regards to the latent hazard anticipation. The second point, which I did not mention clearly, is about the glance duration. Both average and total glance duration is consistent with past literatures, which says that total glance duration, the middle-aged drivers do better than the younger drivers, which means they glance more, and on an average they glance the same amount of time. The third point is about sim sickness, which says that driving experience there's a main effect of driving experience or age, which is consistent with previous literature as well. But what's encouraging is that there was no difference of the scores on the basis of the platforms. Post-study questionnaire feedback and results will serve us as an excellent roadmap for improvements during future work. Limitations of the study, we had problems. There is always a problem with between subject experiments to maintain the homogeneity between the participants in different groups. Even with counterbalancing, it's pretty hard to maintain the homogeneity. Within subject, we could have done a within subject experiment, but we wanted to prevent the notion of bias more, and hence we stuck with the between subject experiment. Only one behavioral factor, that's hazard anticipation, and its sub-factors, that's glance duration, were tested and validated. More variables and measures must be validated in order to say that VR is a completely validated high fidelity platform. Evaluation of an older age group needs to be considered to completely eliminate the threat of sim sickness. So our age group was, the middle-aged driver age group was 30 to 54, but it's been reported that above 54 people are more susceptible to sim sickness. So that age group is also of interest to see if sim sickness is prevalent in those age groups in any way different from what we have received on the RTI simulator. Future work and impact, we'll be recreating the risk awareness and perception training program exclusively for VR on driving simulator platform. At least that's what we are looking at somewhere down the line. Now that we have most of the measures for RAPT validated, I think that's the most obvious part to do, to recreate RAPT, but when it will be done is still in question. More measures will be should be validated. Portability ensures training on widespread basis, something not possible with fixed base simulator, which allows us to invest in multiple VR simulators and move it across different places like high schools and licensing places in order to ensure training. Multiple vehicle conflicts involving multiple drivers and multiple road users can be tested due to the open source nature of the gaming engine and also due to the portability. They can be used for licensures to evaluate drivers' crash avoidance skills. So that's all the future work and impact I could think of. I'm happy to receive any questions from you guys. Thank you for the presentation. Thank you for the opportunity of the presentation. I will be viewing the questions now. Don, would you like to?
I was trying to not interfere with your presentation because our mics seem to be interfering with each other. I see that Cole did post a question. I'm going to let you address that first.
All right. What limitations still exist for VR? Would you be comfortable using VR for future simulation experiments? Um, yes, I think I would be comfortable using VR for future simulation experiments. But I still do believe that we need to sort out the vehicle measures that the RTI simulator currently measures, such as lane deviation, speed, acceleration, steering wheel offset, and those measures such as those. The simulated sickness for older drivers than our age group measured here is um, also something of interest. I know we have discussed this because UMass previously did a study on older drivers, and we found out that there was a high attrition rate for older drivers from about 54 and 60 years old. Hope that answered your question, Cole. And which is easier to develop scenarios on? Oh, I'd say obviously the Unity engine, because the RTI's ISA setup like really is 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 limited, to say the least. But yeah, I'd use Unity any day, anytime. It's much more easier to place objects and to make animations on Unity when compared to the RTI simulator. One thing that prevents people on Unity from developing anything is that you need to know a good amount of C sharp to develop stuff on Unity. So once you know C sharp, I think you would love Unity. I think anyone who's used both the RTI software and Unity will tell you the same. Another question I see from Don was about the comparison of sickness rates across the platforms. Don, could you let me know what exactly you were interested to know about the sickness rates? Hi, Chuck. I'll get to your question in a moment. I just want to know what Don asked. Yeah, so for the VR simulator, we had about let's look at the chart actually if my screen is being shared still. So as you can see, for the younger drivers, they actually felt less symptoms than the older drivers. On the VR, it was a little more, particularly because of the prevalence of turns on the in the scenarios. But basically, nobody really felt sick up to the point where they were disoriented or they felt nauseated, which was a very encouraging thing. We had two dropouts during the entire experiment, but they did not cite their reasons as sim sickness. It was more like fatigue and sickness, illness like headaches and stuff like that. But those two participants did not really say that it was simulator sickness. So I think the results we found out from this sim sickness questionnaires are really encouraging. I see that Don is typing more. I'll answer Chuck. Meantime, many traditional simulators spent a lot of effort with the automotive vehicle model and kinematics. What about VR? Chuck, I do not understand your question that well. What do you mean by automation vehicle model? Is it trying to replicate automation on the VR headsets? Oh, okay. Yeah, gotcha. So the acceleration and braking and everything was there was really low latency between. Let's say if I put my foot on the brake, it would almost certainly translate to the avatar inside the VR headset that is the driver putting his foot onto the brakes. It was um, as long as it was pressed and even the slightest of touches were reciprocating inside the VR headset. The acceleration was doing the same as well. There was a slight latency with the steering wheel motion. Um, the view that the participant took to their right were also similar to what the view looked like inside the simulator. Were those values default in Unity or did you program them? Actually, I went through a fair bit of programming to get them to have the same values. Uh, Not like a real car which has inertia, etc. Yeah, so yeah, I do not know how to answer that question. I'm sorry, Chuck. I'm pretty sure I'm not understanding the question properly, but I'm really sorry. Sure, Jack, thanks. Um, well, I had to say that the controls were just so that I try to answer the question. The controls on both simulators were quite the same, apart saying that the input values are the same, the acceleration was the same amount of force on the gas resulted like let's say I pressed a little bit, pressed gas a little bit and took me about 30 miles per hour on the simulator. It will also take me 30 miles per hour on the VR driving simulator as well. But at the same time, the general feel of the setup was more similar to of the setup of the VR simulator was more similar to a gaming setup rather than an actual car. So participants did complain that they did not feel like they were inside a car, even though they felt very immersed in the environment. They felt like the setup was more like a gaming setup. Like they told me repeatedly that they felt like they were driving a Mario Kart. So um, I'm still not sure if I answered your question right, but yes, exactly, Chuck. You got it. Thanks, Cole. Thanks, Chuck.